Okay, we're now looking at Newton's method of approximation, and this is exercise 9.2. Now, Newton's method is a different way of approximating the root of a polynomial equation. It generally gives a more accurate approximation than the method of halving the interval, and as well it takes fewer steps to get to this approximation. Okay, so notice with halving the interval, sometimes you had to do it twice or 3 times, okay, to get a fairly decent approximation. However, with Newton's method, it's often a lot quicker. Now, if we've got a function in x here, now the function is this curved bit here. I'm just going over it now. Okay, so it's that curved bit there. So that's your function, and here's your root. So your root is where your function cuts the x-axis. Now we can see this line here. Now what I'm tracing here, just watch, this is a straight line. It's actually a tangent. This line here, this straight line, is a tangent to your curve at the point A. Okay, and so when x is A, here we've got the tangent to the curve at point A. Now the tangent cuts the x-axis here at A1. Okay, so it says if x equals A is close to the root of the equation. Now here's the root of the equation, and here is x equals A. Okay, so if x equals A is close to the root of the equation, function of x equals 0, then the x-intercept A1, so that's it there, the x-intercept A1 of the tangent at A is usually closer to the root. So here is the formula for working out what this value of x is at A1. So A1 is, we use this formula, it's the value of A, so it's this x value here, minus the function of A, so you have to substitute this x value into the function to get the function of A, over f dashed A, over the first derivative of the function, and you substitute in A, where A is close to the root. Okay? Okay, now for some notes. So, exercise 9.2, Newton's method of approximation. Let's say this is your function, okay? And here is my root. There's my root, okay? We'll just pick some point A, okay? And we will, sorry, it's about there. We'll do the tangent at A. Okay, and this point here, A1, which lies on the tangent at A, so this is the tangent at A. Okay, here is my function, so this is my function y equals function of x. Okay, this point here with the big circle there is A comma function of A. That's what that point there is, A function of A, because it lies on the curve. And this here is the tangent at A, and this here is A1, which is the x-intercept of the tangent at A. Now, to find the approximation A1, the formula is A1 equals A minus function of A over f dashed A. Okay? Where A is close to the root. Now, there are times when you do this where your approximation for A1 will actually be further away than A, but I will do that in our second lesson on this. Okay, so we're just going to start with the basics. For now, we're not going to look at the cases when this doesn't work. Sometimes you actually end up with a worse approximation, but it depends on the shape of the curve at that point A, whether it will work or not. But we'll do questions like that in the following lesson. Okay, I'll just do a couple of examples now. Okay, now here is the proof of the rule. So here I've got my function, it's the curved function. Here I've got my tangent at A, and this point here is the point A function of A. Now if P is the point A function of A, and if it's a point on the curve y equals function of x, and R is the point, or is the x-intercept of the tangent at point P, then the gradient of the tangent of the curve we know. Remember, when you're doing gradient of function or gradient at a particular point or gradient of tangent, it's always the first derivative. So the gradient of the tangent to the curve is given by f dashed x. Now, that's the gradient of the tangent at any point on the curve, but the gradient of the tangent at point A is f dashed a. So therefore, the equation of the tangent, remember you need the point gradient formula, it'll be y minus y1 is equal to m bracket x minus x1. Now, here's our point. That's x1, y1. So it'll be y minus function of a equals the gradient at point A, which is f dashed a here, bracket x minus a. So we're using the point gradient formula, where the point is a function of a, and the gradient of this tangent is f dashed a. So at R, at this point R, we know that this has an x, y value, but the y value happens to be 0. So at R, y is 0. So we substitute y equals 0 in here, and we get 0 minus function of a, just what I've highlighted here, equals f dashed a x minus a. Expanding this, we get f dashed a x minus a f dashed a equals negative function of a. Now, if you take the a f dashed a over to the other side, we get a f dashed a minus function of a is f dashed a x. And if we divide through by f dashed a, we'll end up with just x, and we'll get all of that over f dashed a. Remember, this can be written as two separate fractions, so all of this can be written as two separate fractions because you've got a f dashed a on f dashed a, and then you've got function of a over f dashed a. So a f dashed a on f dashed a, the f dashed a's cancel here, and that just becomes a, okay? And here we've got function of a over f dashed a, and that stays the same. So therefore x, okay, the x value at R is a minus function of a over f dashed a. And that's how we prove Newton's formula, that formula for approximating the root, okay? So therefore the x-intercept a1 here of the tangent is a1 is a minus function of a over f dashed a. Now, several applications of Newton's method will often give a closer approximation, okay? There are some examples here in your textbook. I'm not going to do those examples so that you can look at them later for more examples, okay? But what I'm going to do some examples from the exercise. So what I want to do is, I just want to look at this investigation first before I do some examples from the exercise. Now, I was saying before that sometimes Newton's method of approximation doesn't work, or you end up with worse results than what you started with. So here's my function here. Now, it's the curved function, and here's my value a, and there's my tangent at a. Now, it seems that where the tangent at a cuts the x-axis at a1, it actually seems to be further away from the root. See, this is the root. This is where the function, here's the function, and where I've got my cursor now is where the function cuts the x-axis, so that's the root. So choosing this point a here is not giving me a good approximation to the root, because the tangent at a ends up over here, and this point a1 is actually further away from the root there. This actual point a is actually closer to the root. So sometimes in some questions you will get answers that are actually further away from the root than the original value of a that you chose, and it will be because of situations like this, okay? All right, now, perhaps if a was actually drawn on the other side, you may get a closer, or it could be a further approximation, I'm not sure, unless I get in there and draw it myself, okay? Let's look at another example here, okay? Now, here is my curve, this concave down parabola, and here is the point A. If I choose this as the point A, and there's the tangent at A, well, that tangent at A is actually never going to cut the x-axis, so a1 can never be found. You'd need to actually have the point A maybe here where my cursor is, for example. If a was here, then I draw a line up here, and then I can do a tangent down there. Or to look at this root over here, maybe a should be over here somewhere where my cursor is, again a tangent there. Okay, but this is obviously a very bad choice for the point A, because the tangent to the curve at A is horizontal, and therefore it'll never cut the x-axis, so it'll never come down like this, or it'll never come down like that. So therefore, in that case, A1, A sub 1 cannot be found. Now here is another example where here I've got a curve, and if this point A is chosen, if we look at the tangent at A, well, it appears that A is closer to the real root, which is just there, and A1 is all the way over here. Now the distance from A1 to the root here is greater, than the distance of A to the root. So the x-intercept at A1 is too far away from the root in this case. In other words, A is a better approximation to the root than A1 is, okay? So this is an example where Newton's method won't work, because it'll actually give you an approximation that's further away from the actual root, okay? All right, we'll now look at some examples. Just change a plan. Before I go through some questions in the exercise, we'll just quickly look at these examples. Here's the first example. Find an approximation to the root of this equation using Newton's method once, starting off with an approximation of x equals 0.5. Of course, you'd need to make sure you write down the formula. Remember, the formula is a1, which is your first root, is a minus function of a over f dashed a. So you need to start working out what function of a is and what f dashed a is, okay, before you can then plug them into the formula. So first we're doing the function of a, function of 0.5, because you're told that you're starting off with an approximation of 0.5. So function of 0.5 is negative 0.375. You have to differentiate the function. So the derivative of this would be 3x squared plus 1. So f dashed x is 3x squared plus 1. Then you do f dashed 0.5, substituting 0.5 in here, and you get 1.75. Then a1, meaning your first approximation, is a minus function of a over f dashed a. Substitute in your value of a, which is 0.5, minus function of 0.5 over f dashed 0.5. I would work these out first and then just substitute as they have done here. 0.5 take away negative 0.375 over 1.75. You'll end up with an answer of 0.714. So you were given that an approximation of 0.5. That was approximately an approximate root. Now, if you put 0.5 in there, you get, what do you get? You get minus 0.375, and A1 is 0.714, okay? So remember, A1 is just a point on the curve, 0.7, sorry, no, it's not a point on the curve, it's the x. We're thinking it's very close to the root. So now, to be able to tell whether this is a good approximation or not, just look over here. You should look at, so function of 0.5 gave us negative 0.375. Remember, we're trying to get the function of the value that you put in to be as close to 0 as possible. If we look at the function of 0.714, just look at it over here. I'm not sure if you can see it very well. Okay, now, the function, sorry, I'll just move it over here. One sec. So if you put 0.714 into your original equation, which is x cubed plus x minus 1, right? So you put 0.714 into this, okay? We're trying to get a result as close to 0 as possible. You'll end up with approximately 0.079. So therefore, your answer of x equals 0.714 is a better approximation. It's actually quite a good one, because this is actually almost 0. Okay, so it is a good approximation, whereas the first approximation, which happened to be 0.5, was actually a fair way away from the root, because function of 0.5 was negative 0.375. Okay, now we'll look at example 2. Now, there are some questions like this first question where they give you an approximation to start with, which is x is 0.5. So you use that for your value of a. But in some other questions, like question 2 here, they don't give you the first approximation. But what they tell you is, they'll ask you to sketch it and show that one of the roots, So sketch that and show on your sketch that one root of this equation lies between 4 and 5. So what you'll do when you substitute x is 4 in, you should get a negative answer. And when you substitute x is 5 in, you should get a positive answer. I mean, if you want to do a quick sketch of that, you can do the axis of symmetry. If you asked to sketch it, you know it's concave up. You can do axis of symmetry. X is negative b on 2a, so it's 4 on 2 times 1, which is 2. When x is 2, you're going to get an approximate y value. They're saying that one of the roots lies between 4 and 5. So if one of them lies between 4 and 5, that's more than 2 units, or between 2 and 3 units from the axis of symmetry. This other side also, this other root, remember it's symmetrical about the axis of symmetry. So the other root would lie between 2 and 3 units away from your axis of symmetry as well. Okay? Now, so to show that your root lies between 4 and 5, you could do it by the sketch, but what I would do, function of 4 here gives you that 4 squared is 16 minus 16, that's 0 minus 1. So function of 4 is negative 1. And if we do function of 5, we get 25 minus 20, which is 5 minus 1 is 4. So function of 5 is 4. And that way we can see that you've got a root lying between 4 and 5. So you can even formally show that by doing function of 4 and function of 5. Then it says, by choosing an approximation of x is 4.5. So let's say they didn't tell you that by choosing an approximation of x is 4.5. If they just tell you that the root lies between x is 4 and x is 5, you just you find the halfway point to find your first approximation, okay, if they don't give it to you. But in this case, they have. So it says by choosing an approximation of x is 4.5, use Newton's method once to find an approximation. So again, using the formula, a1 is a minus function of a over f dashed a. Work out function of a first, then work out f dashed x, then work out f dashed a. In this case, a is 4.5. So we've got function of 4.5, substituting it into the original equation, you get 1.25. F dashed x, if you differentiate this function here, you'll get 2x minus 4, which is here. F dashed 4.5, substituting x is 4.5 into that, you get f dashed 4.5 is 5. Here's your formula, a sub 1, is a minus function of a over f dashed a. Substituting in this value for function of 4.5 and this value here for f dashed 4.5 into the equation, you'll get an approximation to the root being 4.25. Now, let's see. Now, function of 4.5 is 1.25. Let's look at what we get for function of 4.25, okay? So function of 4.25, we're seeing if that's a better approximation than function of, than 4.5 is. So on your calculator, you'll just substitute 4.25 into here, and you get 4.25 squared minus 4 times 4.25, take away 1. My answer is 0.06. Now that is almost equal to 0. So when I do function of 4.25 to check my answer, I get 0.06225 actually, to be exact, and that is a very close approximation because that almost equals 0. So that's a good answer. Here is question 3. Now it says find an approximation to the root of cos x equals x on 3 near x is 1.1. Now we know that cos x equals x on 3. Remember, to find the root of this equation, you take everything over to the left and you'd put it equal to 0. Now actually girls, this equation, you actually can't do this question because we haven't learned how to differentiate cos trig functions, okay? But if you want, you can look at your formula sheet, and if you differentiate cos x, you'll actually get minus sine x. So if you want, you can try it and use your formula sheet. Otherwise, we'll do questions like this once we've done our trig functions, okay? Now, in this question here, So what we'll do at the moment, I think we'll just leave any functions. Now let's look at this other example. It says find an approximation to the root of this equation by using Newton's method once and starting off with an approximation of x equals 0.2. So again, we do function of 0.2 by substituting it into this equation, and we get negative 0.792. We'll differentiate, find f dash x, and that would be 3x squared plus 1. And then we do substitute 0.2, our approximation, first approximation, into f dash x. That will give us f dash 0.2, and we're getting 1.12. Now, we write out our formula. A1 for the first approximation is a minus function of a over f dash a. So it's 0.2 minus function of 0.2 over f dash 0.2, substituting these values in, and I'm getting 0.907. Now my first approximation was 0.2, okay? Now let's have a look. If I put 0.907 into the calculator and substituted x is 0.907 into that function that I've highlighted, I get the following: 0.907 cubed plus 0.907, take away 1, I actually get 0.653. Now, whereas before I was getting 0.792. That actually probably is a little bit closer to the root. Well, we're getting, but it's not close. It's actually a bit closer than that, but it's not close. See, if you do function of 0.907, I'm getting 0.65, which is not very close to 0, so it's not a very good approximation to the root. Now it says, over here, if we look at this bit over here, it says the root lies between x is 0 and x is 1. And the approximation of x is 0.2 is not a good choice because it's too far from the root, okay? So obviously that's probably not a very good value. Maybe something like 0.5 might have been better, or some other value, okay? I'm going to do an example from the exercise 9.2, question 3. It says this polynomial equation, 4x cubed minus x squared plus x minus 2 equals 0, has a root near x equals 0.6, and use 2 applications of Newton's method to find an approximation to the root, correct to 3 decimal places. Okay, let's start. We've got the function of 0.6. Now that's 4 times 0.6 cubed minus 0.6 squared plus 0.6, take away 2. Get your calculator out and work that out. So 4 times 0.6 cubed, take away 0.6 squared, plus 0.6, take away 2. I'm getting an answer of negative 0.896. So we've done function of a. Now we're doing f dash x. So differentiating this function, and you will get 12x squared minus 2x plus 1. So f dash 0.6, substituting 0.6 into your derivative, and you will get 4.12. And so therefore, your first approximation, you know, a1 equals a minus function of a over f dash a. Now, your values are 0.6 minus now the function of 0.6 over f dashed 0.6. So we've got 0.6 minus, or take away, negative 0.896 over 4.12. And so you'll get, you can just do 0.6 plus. So 0.6 plus 0.6 plus 0.896 divided by 4.12, and you get 0.817475. So 0.817475, etc. Okay? Now that is your first application. Now for your second application. Okay? So now we're going to use the approximation 0.817475, etc. I'm going to write a new formula. Instead of writing A1 is A minus function of A over f dashed A, I'm going to write A2, meaning it's my second approximation, is A1 minus function of A1 over f dashed A1. Okay? So continuing over here, A2, meaning my second approximation. Now, function of A1, I don't know what it is, so I have to substitute that in. So let me just work those out. So that's my second formula. Okay, so function of A1, need to work that out. So we just substitute in, so that will be function of 0.81745, etc. Just putting that into the original equation up there. So here's your equation, 4x cubed minus x squared plus x minus 2. Okay, so just putting that value in there. So we've got that value cubed, I've just kept it in my calculator, times 4 minus 0.817476 as an approximation squared plus 0.817476 is an approximation minus 2, and I'm getting 0.33. So I'm getting that the function of that is I'll just put it down here, 0.334376. I've rounded that off a bit. Okay, now f dashed of your value of 0.817476 or whatever it is substituting that into your f dashed equation, we get 0.817476 squared times 12 minus 2 times 0.817476 plus 1. So f dashed of that first approximation there that we got is 7.384252, and so therefore the second approximation is A1, which is 0.817475. You probably don't need all these decimal places, okay? Probably carrying, look, we want our answer to 3 decimal places. Actually, it's probably best to have more than 3 here, okay? Minus f function of A1 is this answer down here, minus 0.334376 over the function of f dashed A1 is this here over 7, so this answer is 7.384252. Okay, so working that out, I've got 0.817475 take away 0.334376 divided by 7.384252. And the answer I get is 0.772. Okay, so that's the second application of Newton's method. Okay, now let's see if this is a good approximation to the root. So I'm going to substitute 0.772 into my original equation. So 0.772 into this. So I've got 4 times 0.772 cubed minus 0.772 squared plus 0.772 minus 2. And if this answer is close to 0, and it is, I'm getting 0.016. So the function of that is 0.016, and that is close to 0. So therefore, this answer here is a good approximation to the root. Let's look at 0.817 and put that into that equation, 4x cubed minus x squared plus x minus 2. So 0.817, I'm going to do that now. So 4 times 0.817, I'll put an extra decimal place, 0.8175 I'll put, cubed minus 0.8175 squared plus 0.8175, take away 2. See, the answer I get when I put this first approximation in, so if I do that, actually here's the answer, 0.33, sorry, it's already done. So if you do the function of this first approximation, you get 0.33. See, that actually, that 0.33 is closer than the first root of 0.6, okay? So that's how you can tell. So that's the first root. Sorry, the fact that this is close to 0. So function of 0.6 is 4.12. Sorry. The function of 0.6 is, sorry, I keep saying the wrong thing, is negative 0.896. But the function of your first approximation, see, that's the function of the original approximation that you're given. Your first approximation, A1, is here. And the function of that one is 0.33. So that's getting closer to 0. It's good. Here's my second approximation. It's 0.772. Now the function of 0.772 is 0.016. So that's actually quite close to 0. So this is a good approximation. Okay. Okay, now for the questions that you can do. I think we'll leave questions 1 and 2. Let's do exercise 9.2, question, let's start off on question 5. Okay, so do exercise 9.2, question 5. Then we'll look at question 6 because, oh, actually no. Then you can do question 7 because it's actually asking you to find the root of that equation a few different ways. So question 5, then question 7, then I think you should do question 8, and try maybe one of the question 9, maybe question 9A. Okay, you can do question 9A. Then we might do the rest, except for any with sine and cosine. So then you can do questions 10 through to 10 to 12, don't do 13. And you can do 14. So 10 to 12 and 14. Don't do question 13 because it's got tan in it. And don't do question 15 because it's got cos in it. Okay, so I'll just show you which questions again. Please do exercise 9.2, question 5, 7, question 8, question 9A, questions 10 to 12, and question 14.